ASP 1.1 of no when should I start? But let's talk. Let's start. So you got email from me earlier about the syllabus and the topics that we're gonna cover probably. Of course, it's a summer time. Also, we don't know how far we can go in this course, but we'll do our best to cover as many topics as we can because they are all important. But what I have in my mind also is to have statistical analyses of stochastic processes involved with little bit in the study, because usually this doesn't happen. You know, usually I took the same course in Cincinnati. I was in PhD, and then I just joined it for it was master level, and this is the same textbook they used there. Introduction to Stochastic Processes. At that time, we had only the first edition by Gregory Lawler, and we covered most of the many sections in this book, but in two quarters. At that time, we had quarters, like we had 3 quarters for academic year. It's not 2 semesters, 3 quarters. And this course was given in 2 quarters, about 6 months. So that's why I'm saying we will do our best to cover everything, but we don't know yet how far we can go. We'll keep going till we stop. That's the point. We'll have R involved as much as we can. That's why also I sent those slides. Usually learning, as you have seen, learning R with tasks is better than learning R for R. So I'll give you the code. We'll learn the code together. We'll see the data, and then you'll see how what we are talking about abstractly. It's not very abstract, but abstractly, like a matrix. How can you estimate that matrix? When we start talking about the Markov chains and the transition matrix, as you're going to see today or tomorrow, what's the transition matrix? How can I estimate it? I have data. How can I find that transition matrix? Talking about transition matrix and processes, infinitesimal matrix require some knowledge about logistic regression and log linear regression. There is one straightforward way; it's going to be very easy, and another one is going to be kind of a little bit advanced. I don't know if you guys studied logistic regression and log linear regression before or not. You did, right? Yeah. So I'm gonna tell you very quickly what is it for, but of course these are textbooks or these are separate classes. I'll try to bring these to the class. For the on-site, of course, I'm going to teach both of them, the on-site and the online, together in this room. So I'll be limited in space. I'll be next to the document camera as it happens. But feel free to ask any questions. Stop me anytime. These questions, I repeat them for the online students because they might be something important also that online students want to understand as well. It might be really a general question. You can contact me by email. My office hours are Monday, Tuesday, Wednesday, Thursday from 1 to 2. And again, this is the primary textbook, Introduction to Stochastic Processes. That's the primary textbook, Introduction to Stochastic Processes by Gregory Lawler. Secondary textbook, you don't have to get it. The first one you have to, I think you have it now, the first one, the main one, the primary one, because the homework will be from that textbook. Okay, I'll say do, for example, the first homework, I know the first 2 problems, do 1.1 and 1.2, page 39. So that's why you need this textbook. I know you have it on Facebook now, right? Okay, so please share it with by email. Okay, share it with everyone. Okay. The second one also you have it on PDF, right? You have it as a PDF. Yes, yes. And but again, we will only look very quickly at specific topics because it's bigger than just having it within another classroom or another course. So we'll have some examples from there. Some after I discuss the material of the stochastic processes, then tell you, for example, let's now find the example where we can estimate the transition matrix. You will understand. We don't have really to cover the whole material. We go to the example and see how can we do that, and you'll find it. I'm sure you'll find it very elementary. Our software is available online. You can download RStudio. You can download RStudio, and I'm gonna share then the codes with you guys. And again, here I'm saying depending on the time and the pace, the statistical analyses will be presented. But the main target is these topics: the Markov chain, Markov processes. Is it clear on that? Markov chains, Markov processes, Poisson process, renewal processes, Brownian motion, and diffusion. If you have taken other courses like with me, like mathematical modeling or statistical computing, you should have heard about these things: chains, processes, Poisson, renewable. Brownian motion you did. Somehow I could squeeze it. Actually, yeah, even diffusion. Yeah. So you had to do diffusion. So you are ready, guys, for the exam. But we'll have more details, more systematic study, not just having them as a subtopic. These are the main topics. That's why we'll work slowly and discuss them. Outcomes, I said here, to be determined, but they are to learn everything. I want to make sure that you guys will learn. Don't worry. Important dates, there are no exams. So there are no big dates that we have to keep an open eye for. But Census Day is Thursday, June 8th. Drop deadline is Friday, June 30th. And there is no class on Independence Day and no class on Study Day. I know some of you can watch the recordings online, but I would ask you to come to the class. It's way important than anything. Attendance is very important, and those who are attending online, it's better to watch every voiceover every day and participate in the discussions if we have discussions. Do 5 homeworks. We'll have 5 homeworks, and the 5 homeworks will be collected after the weekend, and probably I'm gonna assign the homework one bit at a time, So, for example, I finish the class today, and then I tell you do 1.1, 1.2. Tomorrow I tell you do, for example, 1.3 and 1.4. Then I'm gonna collect them on the next Monday. Okay. So each one will be for 21%. So 21 times 5 is 105%. From 90% to 105 is A, B, C, and the rest is F. Okay, question? Yeah. Okay. You mean you wanna do the homework using LaTeX, right? What code? Our code. We don't have much our code homework. Okay. Okay. That's a kind of secondary objective. So I'm not gonna talk about it now. The main objective is really just stochastic processes. Okay. Okay, Markov chains, Markov processes, Poisson processes, renewal processes, Brownian motion, diffusion. Okay, that's the main goal. R might come as a side, but it's not the main thing. We might have a homework. Then you'll submit the homework online using Blackboard. Okay, just like we did before. You go to the homework folder, and then you upload. You'll have the link to upload your homework. Use handwriting, use LaTeX, use many files as you want. That's okay. If you want to scan the homework, send it to me by email. That's still okay. Okay. Uh, yes, but still there are some difficulties or differences that I don't know. I have to adapt to yet. Okay. There are no makeup for the homeworks, and you can of course stop me anytime, ask me questions. We'll have only 5 homeworks, and of course we have all to observe scholastic integrity, honesty, integrity, respect, attendance for on-site is mandatory. So we are missing one now. Okay. If you have any disabilities, any questions, any concerns, please let me know so we can arrange for accessibility. I have to report sexual harassment, discrimination, and violence according to the rules and the bylaws. Do you have any questions? Okay. 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 I'll do. Okay. Now, stochastic processes. So let's start first. Of course, I shared with you guys 2 files. One again for R, and the other one for probability background. It must cover even more than what you need for this course. But it's good to refresh your memory about probability and the statistics. And if you really studied these slides, you will feel more relaxed. Other topics that we'll need for this course are matrices, algebra, solving the equations, differential equations sometimes, um, and finding eigenvalues and eigenvectors, finding limits, integration, summation. So it's kind of that kind of applied course that you use different concepts and skills that you learned during your elementary school. And we start again by saying first when. Can you are you using this laptop? Okay. Are they there on the laptop now live? Okay. 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 But we are not gonna go over them. Okay. Number one, let's fix a probability space. I like always to start from a probability space. This is the atom of everything, a probability space. It's made from the triple, the omega, the sample space, which is a set of all possible outcomes of a random experiment, and the sigma algebra, which is the family of all events. Okay? The power set is a sigma algebra. The power set is the family of all events, actually the all subsets of omega. The power set is the family of all subsets of omega. It's a sigma algebra, and it could be considered as the family of events. But here we might restrict to a sub one. It's not the whole power set. So let's just fix this. This is just technicalities. Let's put it that way. Omega is the sample space. F is the sigma algebra, which is the family of all events. And then there is a measure. We call it probability. Okay. Any random variable, any stochastic process, as we will see later, are measurable or defined with respect to this probability space. So technically, we are talking about one world here. There is again sample space, sigma algebra of subsets of this sample space. It's a sigma algebra, and it constitutes the family of all events. P is a probability measure. Of course, as a sigma algebra, it's closed under completion, countable union, and etc. P is a measure, so we know that The probability, of course, of omega is 1 because omega itself is an event. Probability of phi, the empty set, is 0, and we know that uh, 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 additive function. If we have A1 and A2 are disjoint, then probability of A1 or A2 is probability of A1 plus probability of A2. Probability of of phi is 0, etc. All of them, you can find all of these in the slides. But we have first to fix a probability space. Next, let's start with stochastic processes. Now, if you have a family of random variables indexed by 0, 1, 2, etc. Or simply, let's write them as xn such that n takes value 0, 1, 2, etc. This is a family of random variables. Each one of these random variables is measurable function with respect to this probability space. Okay? That's, again, technicality. But we know what's a random variable, right? We know what's a random variable in general. It's sometimes at low level probability we say it's a numerical outcome of a random experiment. But originally it's a function from omega to r. Okay, that's the definition, the mathematical definition of a random variable. Okay, let's say this is a discrete, we call it a discrete time stochastic process if xn as a random variable maps or a function of on omega into some set, let's call it S. S is nothing but what we call state space. We called it discrete time because, as you can see here, the index is discrete. It takes values x0, x1, x2, etc. at discrete times. It has discrete state space if S itself is discrete, just like if S is a set of 1, 2, etc. up to, say, some finite n. Then it's also discrete state space. Because some processes have continuous time, continuous state space. Some of them have mixed, like discrete time, continuous state space. Some of them have discrete time or continuous time, discrete state space. But I'm starting with the simple one. We have here discrete time and discrete state space, which means we are kind of talking about a sequence of discrete random variables. That's a sequence x0, x1, x2, etc. And each one of these random variables are taking values inside a discrete set. So it's a discrete random variable. It's a discrete sequence of discrete random variables. But the right way to say it or to define it, it's a discrete time stochastic process with discrete state space. Of course, this is somehow restricted. It could be 0, 1, 2, all the way up to n. That's another example. It could be, in other examples, it could be negative n all the way up to n. But we would like always to think about this one just for brevity and for easiness of presentation. When we talk about discrete state space, let's talk about this one. But in some of the examples, as you're gonna see later, we're gonna talk about 0 through n. We'll talk about even vertices on a graph. They don't have to be really numbers on like integer numbers like this. They are just discrete and finite. Okay. Finite, because as we'll see now, we are heading to talk about finite, or this is the main topic, finite of chapter 2, finite Markov chains. Finite Markov chains. So in general, this is called a stochastic process, discrete time, discrete state space. Let's see in a few seconds. We'll show you what do we mean by a Markov chain, and we call it finite because it takes finite values. Okay, if it takes any integer number, we would call it countable. If it takes values or the time is in continuous time, we call it process. We call it a chain because we have discrete time. Finite state space, discrete Markov chains or Markov chains. In here, in this end, before we go on, is usually the time index or the time, but that's again for simplicity or for brevity, so we can, or for convenience of illustration and presentation, we call it time. But n might be a point in space. Okay, this process might be walking in space, and it might have both of them, time and space. Okay, just like the fusion. Okay, it might have both time and space. But this one, for brevity, this is the time, and the time here set t is nothing but 0, 1, 2, etc. And n is in that time or index set. In general also, we say X node is the initial state. That's where the process started. Okay? X0, while it's random, it's the initial state of the process. It's where they started. Again, I would say it's random, unless I state how much is it, or where was the process at time 0 with probability 1. The main target of all of this is the following. The target is the joint distribution. It's as simple as we have learned in probability, multivariate multiple random variables. It's just the joint probability distribution. That's our own goal, is to study the joint distribution. And the joint distribution of the process up to time n is given by probability. X node is I node. I node is any number inside the state space. Okay. Comma, x1 is I1, comma, x2 is I2, comma, etc. up to the last one, xn is equal to in. Of course, n changes. N runs from 0 to infinity for any n equals 0, 1, 2, etc. We want to study this joint probability distribution. They are discrete random variables, so I can call it naively joint probability mass function. Okay, how can I study this joint probability distribution for all n and any ij in S in the state space, and j is 0, 1, etc. So how can I find it? Usually in probability, we are given the joint PMF or PDF, and then multinomial, multivariate, normal, etc. But this is a stochastic process, and x1 is supposed to influence, or sorry, x0 is supposed to influence x1, and x1 and x0 are supposed to influence x2. x1 and x2 and x3 are supposed to influence x3 in general. We are still talking about stochastic processes in general. Okay. Later, when we define Markov chain, we'll find that not all of them are influencing each other, as we will see. So, in general, in stochastic processes, these are not independent, and they are influencing each other, where the whereabouts of the initial position of the process will influence where it's going to go next. And at this step, and that step, they might influence where is it going to go next, and so on. Okay, so that's the main target. Before we address the main target, let's talk about the initial probability distribution. Why the initial? Because again, from where the process starts is going to influence where is it going to go. The initial probability distribution. Let's call it phi0. That's the probability distribution. And phi0 of I, or phi node of I, is the probability that the process starts at state I at time 0, or I belongs to S. So it gives weight to every state in the state space that tells you what is the probability to start from either one of these states. Okay? And you can always imagine a system that is changing over time. Imagine the weather. Today it's raining, tomorrow it's dry, the day after it's dry, the day after it's raining. So the system here is the weather. The probability that the initial day or the initial state of the weather is raining is given by phi0. The probability that the initial state of the weather is dry is given by phi0 of dry, and so on. So phi0 will give you the chances of the probability of where the system or the weather will be initially. Okay? You can also consider a system. You can consider your own mood. You know, today I'm happy, tomorrow I'm sad, the day after I'm neutral. If we start the process from tomorrow, I cannot really tell which state I'm going to start from. There is a chance I'm going to start from happiness, sadness, or neutrality. So we need a probability distribution to tell us from where the process is going to start. This is called the initial probability distribution, or phi0. I can place, since S is finite, countable, and discrete here, then I can write down probability vector, or initial, we're going to use it later, initial probability vector given by phi0 bar. This is how I'm going to follow the notation of the textbook. Phi0 bar is given by a vector of phi0 of 1, comma, phi0 of 2, comma, etc. till the last one, phi0 of n. Remember that we choose S to be given by 1 through n just for convenience of instructing you guys. And actually the book does the same thing, but we can generalize. S could be running from 0 to n or whatever, as long as it's finite and countable. So finitely countable. So this is called initial probability vector. As you can see, since each one of these elements is a probability, each one of these phi0 of I is between 0 and 1, and they add up, all of them must add up to 1, because they are probability. Okay? Again, the goal or the target is this one. But we still need the initial probability distribution to talk about the joint probability distribution of the process. Okay? That's why we're going through that. Now, let's try to establish the formula for the joint probability distribution of a stochastic process. Let's do it in steps. Let's do it by induction, one step at a time, so we can understand how it will look like. Let's start with n equal to 2, just two of them, two steps, 0 and 1. Sorry, n equal to 1. Let's start by the joint distribution of x0 and x1. Okay? It's the joint probability distribution of the sequence up to time 1. Remember, guys, that the probability from the laws of probability, probability of A and B is equal to probability of A times probability of B given A. Right? The same applies here, or the same formula here. It's equal to the probability of A, x0 equal to I0, times probability that x1 equal to I1, which is B here, given A, which is x0 equal to I0. Okay? And the first term is nothing but the initial distribution, right? This is what I defined here as the initial distribution. Probability that x0 is I0 would be phi0 of I0. So here this will be phi0 of I0 times this quantity, this conditional probability. Let's call this conditional probability Q1 of I1 given I0. And this is nothing but what we call the transition probability from I0 to I1. And to be precise, it's one-step transition probability. It took it one step to jump from I1 to from I0 to I1. One step. Transition probability. Okay? So we can write down this joint probability distribution as the initial distribution times the transition probability from I0 to I1. Okay, clear? Okay. So to find this, to describe the joint PDF of the process, of the whole history of the process from 0 to 1, of course it's a short history, but to find the probability of this trace of evolution in this stochastic process, you need the initial distribution and you need the one-step transition probability. But that's so simple example. Give us the bigger one. Okay, let's see the next one, the general one. The probability that x0 is I0, and then moving to I1, then moving, the system moves, or the process moves to I2, all the way up to IN, could be found by a similar way, using the similar formula that we discussed here and same process. How? Let's see. After we do this, we would say we are done. We succeeded in our goal to find the joint probability distribution of the trace of the process throughout its course, from time 0 to time n. Because remember, in probability, we studied distributions, probability distributions. Why? Because once you get the probability distribution, you can talk about probabilities, calculate events, calculate the probabilities for events, talk about the mean. You can talk. So you can do lots and lots of things when you have the probability distribution. That's why we are going through this. But of course, you will see later we'll diverge a little bit. But let's do this. Let's do it the same way, but by induction. Let's consider this whole first n-1 term as A, and this last one as B. And let's do the same thing here. Probability of A and B is probability of A times probability of B given A times probability of B given A. And let's call, or let's have a look at this formula. This one is up to n. This one is up to n-1. So by induction, successively, I can do the same thing for this same term here. Go one more step. Consider this term as the new A, and this one as B. And keep doing this successively. Then it's probability of A up to n-2 times probability of B, this new B, xn-1 equal to n-1 given A times this one, of course. And keep doing this over and over and over till we reach this term. Probability that x0 is I0, just like we started here, times probability of x1 equal to I1 given x0 is I0 times probability of x2 equal to I2 given x0 equal to I0 and x1 equal to I1 times, and then you keep doing this till the last one, which is this one, times probability that xn equal to In given the whole history of the process. So this is done by induction. I hope you can see the similarity. This is just one step. This is the nth step, and this is the n minus 1 step. If we assume the general formula is given by this, then you can move right from here to there. And for simplicity, let's rewrite it as we know now the first term here. The first one here is nothing but phi node, the initial distribution, phi node of I0 times the one-step transition probability from I0 to I1 times the two-step transition probability through I0, I1, which is Q2, I2, given that it went through I0 and I1, times Q3, that it was at I0, then I1, then I2, conditionally, is going to go to I3, and so on till the last one, which is Qn of In given the whole history. This is the formula for the joint probability distribution of the trace of evolution of the stochastic processes. Because they depend on each other, we have to start from, or we would say the probability that this trace will happen, x node is I node, then x1 is I1, then x2 is I2, then x3, all the way up to xn is In, is nothing but the probability it's going to start from I1, I node, then it's going to go in one step from I node to I1, then it's going to go from I0 to I1, then to I2, and then I3 will be reached from I0, I1, I2, etc., times probability that it's going to reach In through I0, I1, I2 up to In. Again, that's for general stochastic processes. And we're done. That's the goal. But how can I find these Qs? Maybe I can assign this. Maybe I can have some restrictions or conditions for this one. Maybe I can observe where did the system start from. I know, for example, today it was dry. Okay? So it started for sure from the dry state. It wasn't raining, right? So the probability it is dry today is 1, and the probability it's raining is 0. So I know the initial distribution. But how can I find these probabilities? Probably we need some more assumptions to simplify these probabilities, and that's what's next, and that's what is about. That's what's all about Markov chains. Markov chains are stochastic processes that can simplify these Qs. Markov chains are nothing but some type of stochastic processes, and one of the most important stochastic processes, again we call them chains because of the discrete time. That's why we call them a chain, not process. Are stochastic processes that satisfy the what we call Markov property. Okay? It satisfies the Markov property, and sorry for the misspelling. And the Markov property says the following. This one, let's take this. Markov property simplifies this Qn. Simplifies the probability that the process will go to In given it was going through this trace of evolution, I0, I1, I2, up to In minus 1. And it says the following: Qn of In given I0 all the way up to In minus 1, which is nothing but the probability that Xn is in a state In given it went through I0, I1, up to In minus 1. The Markov property says this Qn, or this probability, is equal to, it's a simplified assumption, or it's equal to the probability that Xn equal to In given, ignore all of this past and only take the present. Hmm? It's called Markov property. Okay. So, no rest for the time. You'll see later something. You will see it later when we talk about something. So, Markov property says the probability of the future given the past and the present, it's only given by the present, or the future is independent of the past given the past and the present. So I can rewrite it this way: the future, which is this one, and the past, so this is the future, this is the past till this point, are independent given the present, which is this one. So if you want to know the probability that the system will be somewhere tomorrow, all what you need to know is the present. To know the transition of the process for tomorrow, you don't need the whole past. You don't need the present and the past. You only need the present. So the future, which is tomorrow, is independent of the past. It's only dependent on the present. To know where is the process or the system is going to go in the next step, just tell me where is it now. Don't talk about yesterday. So the probability that the system will be in state In given the whole past and the present is only dependent on the present. And this is what makes it a special process, special and important process. Markov chains are very important, very widely used in many systems, in modeling many systems. But again, notice that we started from general stochastic processes. This is the target, to find the joint PDF. Once I find the joint distribution, this is the form. From where can I get these Q1, Q2, Q3 up to Qn? I need some assumptions. Markov came to the picture and said, okay, there are many systems that you don't really need the whole past to know where it's going to go to. You just need the present to tell me where is the next jump. Okay? And in other words, we say it this way: the future given the past and the present is only dependent on the present. Or sometimes this is a better way: the conditionally, or given the present, the future and the past are independent. Given the present, the future and the past are independent. By the way, just to make sure you got this correct, if you have probability of A given B and C is equal to probability of A given C, then we say A and B are independent, conditional on C. A and B are independent, conditional, or given C. If we don't have C, this is the most common one. Probability of A given B is equal to probability of A if A and B are independent. That's from baby probability, right? If you have A and C, then we say it's conditionally they are independent. They are independent, but given another one, okay? Given C. Clear so far? Any questions? According to this new formula, I can simplify this multiplication and rewrite the joint PDF now, or probability distribution. How? Let's rewrite the joint with simplified formula, because now we don't need the whole path in these Qs. I don't really have to have I1, I2. I don't need I1 here. I don't need all the way from I0 to IN minus 2. I only need IN minus 1. I need I2. I need I1. And here I0. So for Markov chains that we have just found out or defined using the Markov property, have the following. The probability that x0 is I0 and x1 is I1 all the way up to xn equal to In is given by phi0 of I0 times q1 of I1, given it was an I0, so it went from I0 to I1, and at time 2 it went from I1 to I2. Notice that I dropped here I0, because the past is not going to tell us anything about the future. Only the present that matters. Here the present is I2. Ignore the past, so it becomes Q3 times Q3 of I3 given I2. I ignored the past, I0 and I1, and do the same thing over and over and over, times till Qn In, given it was an In minus 1. Okay, so Markov property simplified the joint probability distribution of the stochastic processes, but it's still difficult to handle because each one of these Qs are just one step transition probability, but they are dependent on the time they made the transition. This is Q1, Q2 is the transition at time 2 from I1 to I2. This one is the probability of transition or transition probability from I2 to I3 made at time 3, and so on. So we go one step further to even one more simplified stochastic process and call it time homogeneous, which is the default in this course. Time homogeneous Markov chain. By the way, Markov chain from now on, it's going to be MC, okay? Not McDonald's. Markov chain. Time homogeneous Markov chain if the transitions are independent of n. If Qn from In minus 1 to In is independent on the time. For any n. When the transition probabilities are independent of time, then we call the Markov chain time homogeneous. Because sometimes it really matters when was the step of the system. Then it's time heterogeneous or time dependent Markov. Is gonna jump from dry to sunny. Oh, sorry, from dry to rainy during summer or winter. Probably the time or the time step can influence the transition probability. When was it done? In some systems, if we are talking about learning, jumping from between two states might depend on the history or the age of the state or the system, how long it was running. Sometimes, if the system is running for long enough time, it's already have been accumulating learning experience that it's very hard for the system to go down to a very low state. The probability at that time to jump from experienced system to very naive system is very, very small than if we do this in the beginning. Probably if the system was in the beginning, going from little bit experience to naive is very, very close. You know, the system didn't really gain that much learning. But as the time goes on, probably going from the top to the bottom has a smaller probability. So it depends. Markov chain might not be the best one for every system you can model. Okay, or time homogeneity also might not be. Sorry, it's not Markov chain. Time homogeneity might not be the best assumption for every system to model. Right? Sometimes transitions need to depend on time. But as far as this course is concerned, because it's introductory course, we will only talk about time homogeneous Markov chain. Okay? Dealing with time non-homogeneous Markov chains is more challenging. Okay? Not for us at this level. Any questions so far? Okay, let's follow the book and call this lowercase t of in minus 1 and in. It's the transition probability from state in minus 1 to in. That's transition probability. Again, I'm following the book very closely. So if you missed anything, you can go back to the book and read. Okay? I'm not going to go farther than the book that much, except probably for examples. I might bring my own examples. Okay. So let's kind of recap a little bit this part and put it in a matrix form. So probability that xn equal to j, given that it was at time n minus 1 equal to I, or the transition probability from I to j is going to be denoted by b, I, and j. It's the one-step transition probability from state I to state j. Again, we are talking about a stochastic process system that's moving randomly, but in particular, it's Markov chain because it obeys the Markov property, which means the path doesn't influence the next step. Okay? Only the present is what matters. This P probability actually maps S by S into 0, 1. I and J are in S and S, are in the state space. So now we can, for a time homogeneous Markov chain, we can see that the joint is so simple. The joint probability distribution of the trace of the process from time 0 to time n is so simple to write down. It's P0 of I0. The probability is going to start from I0. Then it jumps from I0 to I1 in one step. Then it jumps from I1 to I2 in another one step. And so on. It keeps jumping or keep multiplying probabilities from in minus 1 up to in at the end. This is a very simple formula. Now we can study that joint distribution. Just give me the transition probabilities for that Markov chain and give me the initial distribution. I give you the joint probability distribution, and then we are done. But let's now study the transition probabilities deeply, more with more details. Let's again stick to S that is given by 1 through n, just for brevity. We can place this Bij inside a matrix, right? So let's put all of them B1 and 1, B1 and 2, all the way up to B1 and n. And here B2 and 1, B2 and 2, all the way up to B2 and n. And do the same thing all the way down here to P of n and 1, P of n and 2, all the way up to P, n, and n. So just since you have only finite states, finite number of states, just take this Tij, place it inside a matrix like this, and call this a matrix P, or what we call transition matrix. Okay? We'll see that using matrices and linear algebra will make our life easier in calculations later. So just place all of them and in a matrix, call this P matrix, uppercase P, and call it the transition matrix. As you can see, it's n by n, n rows by n columns. The first cell gives you the transition probability from state 1 to state 1, which means the probability to stay in the same state after one step. And this is the probability to stay in the same state of 2 after one step. So the diagonal gives you the probability of staying in the same state after one step. This probability, P12, is the probability to jump from state 1 to state 2 in one step. This probability, P of 1 and n, is the probability to jump from state 1 to state n in one step. So these are just nothing but one-step transition probabilities from one state to the other. On diagonal, the jump is really to stay, not to jump. This is probability of 1 and 1. Then it says it's raining today. The probability is going to also rain tomorrow. P22, probability it's dry today. It's going to be also dry tomorrow. So on. This P is called a stochastic matrix. Stochastic matrices are general topics. They don't have to be transition matrices. But this transition matrix is a stochastic matrix. B is a stochastic matrix. What does it mean? It means the following. Number one, all of the entries are between 0 and 1. And that's true because they are probabilities, right? The probability of ij is between 0 and 1 for all I and j. Okay? Number two, if you add up any row, the sum is going to be equal to 1. If you add these up, the sum over j equals 1 up to n, probability of, let's choose I, comma j. If you add up the entries of the ith row, the sum is going to be equal to 1. Because this is adding up over all of the possibilities for that process to go to, from I to 1, from I to 2, from I to 3, plus from I to 4, plus from I to 5, till the last one, which means we're adding up all probabilities, and the total probability is always equal to 1. That's why we call it stochastic matrix. A stochastic matrix have sum of rows equal to 1. Okay? But here we have them also between 0 and 1, the entries. You can see from here, we can put this in a matrix form. The last one could be put in a matrix form. This means that P, the matrix B, matrix product, the unit vector, this one is given by just ones, 1, 1, 1, 1, 1. Okay. Yeah, this is the row, and this is the column. Yes. Yes. So you fix a row, you just add up the entries of the row over columns. Okay. And what did I write down? Yes, here for all I. Yes. Okay. So this is the vector of all ones, and it's given by n rows by one column. Okay. This tells you what? Tells you that if you multiply the transition matrix by 1, this whole row will be multiplied by 1. It's like adding them up. And when you add these up, you should get a 1. And when you add these up, when you multiply them by 1, it's going to be 1, 1, 1, 1. So P times 1 is going to be equal to the same vector 1. That's the 1's vector. What does it say? What does it mean here? What does this say to us in terms of algebra, linear algebra? It says that hmm? Yes, you can say 1, this one's vector is a right eigenvector with, how much is the eigenvalue here? 1 eigenvalue. You know the eigenvalues on eigenvectors, P times X equal to lambda X. X is an eigenvector, lambda is an eigenvalue. Since the multiplication here happened from the right, we call it right eigenvector. There is a possibility that Y times, but this time this will be a row vector. If you multiply from the left by a row vector and get another number mu times Y, then Y is called left eigenvector. Okay? This is a left eigenvector. This is a right eigenvector. Lambda here is an eigenvalue. Mu here is another eigenvalue. Okay? So, because we will have another, why I'm talking about these two, right and left, because we'll have right eigenvectors in this course and left eigenvectors. And probably next time we'll see the left eigenvector, which is actually the stationary distribution, as you can. Okay, so 1 here is an eigenvector. So lambda here is equal to 1. 1 times 1 is still the 1's vector. 1 is a right eigenvector with 1 eigenvalue, or with eigenvalue equal to 1. Okay, clear? Just a note, because this will turn important when we prove existence of the stationary distribution. Any questions so far? Okay, yeah, go ahead. Yes, we will do Jordan the conversation, but not today. I'm actually willing to stop here because the next examples are kind of long, and we better to give them their time. We didn't start on time today. Tomorrow we'll continue doing the work. That's just a short introduction. We got together. That's good. Tomorrow we'll continue. So do you have any questions before we stop here? No questions? Not yet. Not yet. There is a homework tomorrow. I'm going to give you a homework tomorrow. Okay, thank you guys. Thank you. Have a good day.